Okay, let's try out one more here. Remember, we're going to go for two equations, and we're going to see what it is that it's asking for. So in airline regulations, suppose an airline policy states that all baggage must be box-shaped with a sum of length, width, and height not exceeding 64 inches. What are the dimensions and volume of a square-based box with, there's a special word, the greatest volume under these conditions? So as soon as I see this word, maximum, minimum, greatest in this situation, what is that telling you? That's a derivative, and what's it the greatest of? A volume. So I know I'm going to have a volume formula, and that's the formula I'm taking the derivative of. Okay, but I have to have other pieces of information in here in order to be able to pull this off. Okay, so suppose an airline policy states that all baggage must be box-shaped with a length, width, and height not exceeding 64 inches. These problems are wimpy problems. Do you really think an airline is going to say the only thing you can ever carry on is a box? No, much less one with a square base. But the purpose of these, yet again, I want to reiterate, the purpose of these is to practice the process so that when things do get harder, and that is something that people do all the time as engineers, set this kind of situation up because you have to figure out what kind of room, right? And how much room do we have and what can we have? And that's why these problems like this are exactly why they put limitations at the airport for your carry-on. Because they have so much space that they can work with. And not only do they have so much space, then they figure out how much volume. How much is this stuff approximately going to weigh? Then that's what they do. That's optimization. How much can the plane carry? That's why you get only so much and so many pounds, right? I mean, all this stuff you guys get. Okay. But the point is, we are going to do our wimpy little problems so you can figure out using this basic here in order to make it bigger, because in Calc 3, you're going to get to do some super cool optimization problems. All right, I digress. Suppose an airline policy states that this must be box-shaped. The sum, what does sum mean? Add them up, right? Is not to exceed 64 inches. What are the dimensions and volume of a square-based box? That's important, because as I make my box here, an artist, I am not. That was not as bad. The fact that this is square base, I know all of my sides are going to be exactly the same, right? And then I have my height, okay? So whenever I figure out my length, my width, and my height here, not to exceed 64 inches, so that means x plus y has to max out there at 64, so we're going to have that equal 64. So 2x's plus a y is 64. Okay, but if I'm taking volume, because that's going to be my derivative formula, right? So volume here is going to be length times width times height, because it's a prism. So volume is x squared y. All right. Remember, the volume is what I'm taking the derivative of, but I can't have two variables. Good thing I've got this other equation over here. So I can take 64 minus 2x and plug that in for my y and then work it. All right, cool, right? Let's scoot this up a little bit because now it's go time. So volume is equal to x squared times 64 minus 2x. And I'm going to figure out my end points, because remember we need the end points. We need to figure out what's the smallest x coordinate and the biggest x coordinate that I could possibly have. So let's set this equal to 0. I'm going to go ahead and factor out an additional 2 from this one just to keep it fully factored. So 0 is equal to a 2x squared, and then I've got 32 minus x, just makes it easier. So x is 0 and x is 32. So I know between 0 and 32, that has to be the dimensions of x for my base. Again, right? We know this is not exact. If I have to have a height, I have to have a base. These are the possibilities, but those endpoints are not realistic. All right. So here I just have something to distribute, so I'm not going to do the product rule. It's just easier. 64x squared minus 2x cubed, and then take that derivative. So what's that? 128x minus a 6x squared. Go ahead and factor. So I'm going to factor out I think just a 2 is in common there, isn't it? 2 and then an x, of course, and that'll leave me with 64 minus 3 with that x. Okay, so when I set, v prime, because it's a derivative, so whenever I set that equal to 0, then x is equal to 0, and 64 minus 3x equals 0. So if I add the 3x, divide by 3, that doesn't reduce, does it? So it's just 64 thirds. All right. So if I'm looking at 0, does that make sense? No, I've got to have something for a length, a width, or a height, right? So my base is a 0. That doesn't make sense. So we're going to cross that off because that's not realistic. We're working actual problems here. What is the actual part of my box? That doesn't make sense otherwise. So x is equal to 64 thirds. Now I want the dimensions. So I'm going to take this 64 thirds and plug it back in so I can get those dimensions. So y is equal to 64 minus 2 times 64 thirds. I'm going to scoot this up so I can see it a little bit better. Oh, that's not as pleasant. Oh, that's not bad. Well, it's not awesome. So y here is now equal to getting a common denominator. The fact that there's a 64 involved with both of these, it's just easier to get a common denominator. So if I have 364 over 3 minus 2 64s over 3, that just makes life easier. So 3 64s minus 2 64s is going to be 64 over 3, 164. All right. Okay, so my dimensions here that I'm looking at, so my dimensions are going to be 64 over 3. Let's bring this down. This is 64 thirds inches, and this is 64 thirds inches. If all of my dimensions are 64 thirds, what is that actually called? It's a cube, right? Yeah. So if I'm looking at this, a square base box, the bottom is already a square. Then if my height is the same thing, that's just going to give me a cube. Yeah. Okay. So the other thing I'm looking at, so therefore, let's write our therefore statement. Therefore, the dimensions, let me make this bigger because I know it's hard for you guys to see that, especially on the video. The dimensions are 64 thirds inches by 64 thirds inches by 64 thirds inches, right? And then if I have the volume is, whenever I'm looking at volume is equal to 64, or the x squared y. So 64 thirds squared times 64 thirds. I don't know what 64 to the third power is, but we know that's 27, right? I don't know what that is. I'm going to cheat and look it up. So here it says it is somewhere around 9,709 inches cubed. If I give you a problem on your test that is somewhere like this, or your quiz or whatever, I am going to give you values that are easier to work with, or I'm going to say, don't multiply it out. You don't get a calculator for that. I don't expect you to work it out in terms of a calculator. So I'm okay if you say the volume is 64 thirds divided by 27 inches cubed. That would be okay. Just because that doesn't make a whole lot of sense. It makes more sense to say that my volume is 9,709 inches cubed in reality, right? So you would have a calculator for that. If you were doing these problems in real life, you would have that calculator. My job is to put tools in your toolbox, and here's tools of how to find optimization. Now I want to point out, both problems we did found the greatest or the maximum. You can also find minimum, and you find it literally the exact same way. All right, so feel free to go and do that. All right, practice these. These are super cool. Have some fun.